Hello everyone, this is Mrs. Whitaker, and today we are going to be discussing the factors that will affect the resistance of a material. So we've talked about conductors and resistors a little bit before, and you should know this from previous knowledge from middle school really. And as a reminder, a conductor allows free electrons to move with little resistance, and it's usually a metal, while a resistor does not allow electrons to flow so easily. And one really big, an extreme example of a resistor is an insulator. So resistivity is the measure of the resistance of an object, of a material. So it's the measure of how much or how little a material can resist the flow of electrons or the flow of electricity. So we actually have an equation for this, and this is in your reference table. And this symbol here is the Greek letter rho, and it's the resistivity of the conductor. This there's a table of resistivities in the reference table. For different types of material. Then L is the length of the material. The A is the cross-sectional area of a wire. We really only deal with wires or tubes for this equation. And as a reminder, the cross-sectional area, it is going to be equal to pi r squared. That's the area of a circle, because it'll be like this, because the L is already taken care of. So if the diameter or radius is twice as wide, the area will be 4 times as wide because of that squared. So again, the chart of resistivities is on the electricity page of the reference table. So this fish symbol right here, this means proportional. And it just means that we can get rid of some of the other stuff and ignore, we can ignore the resistivity, we can ignore rho, and we can just focus on the cross-sectional area, and we can focus on the length. So it means that the resistance and the length are directly proportional. So as the length increases, the resistance will increase. So because it has a greater length, that means that it has more length to travel, and it has more electrons to flow against, to bump up against. So then the resistance increases. The area is, as the area increases, the resistance will decrease. That's because as the area gets bigger, it gives a greater it gives more room for the electrons to flow, so it's not so tightly squeezed together. So that means that that there will be less resistance because they're not rubbing past each other as much. So this is from the reference tables. These are some of the materials. These are at 20 degrees C, 20 degrees Celsius. This is, there's materials like aluminum, copper, gold, nichrome, silver, and tungsten. The resistivity is measured in ohms times meter. And if you notice, it's all times 10 to the minus 8th. And this right here is really important. It says that resistivity changes depending on the temperature. Colder temperature allows electrons to flow better. Warm temperatures slow electron passage. 20 degrees was just chosen because it's around room temperature. Okay, so we have an example. This is just example 1. So it says, during a laboratory experiment, a student finds that at 20 degrees Celsius, a 6-meter length of copper wire has a resistance of 1.3 ohms. What's the cross-sectional area of the wire? So we know that the temperature is 20 degrees C. We know that the length is 6 meters. It's the resistivity of copper is going to be 1.72 times 10 to the minus 8th ohm times meter. The area is what we're looking for. The cross-sectional area is what we're looking for. And the equation we're going to use is R is equal to rho times L divided by A. And we're going to solve for A. So you multiply both sides by A. And then divide by R. So it's A is equal to rho L divided by R. And that's equal to 1.72 times 10 to the minus 8th times 6 divided by, the resistance here is 1.3 ohms. And we get 7.9 times 10 to the minus 8th meters squared. Okay, so it's 7.8 times 10 to the minus 8th meters squared. Now, the temperature does come into play. It's not just a little note. It says, after an incandescent light is turned on, the temperature of its filament rapidly increases from room temperature to its operating temperature. As the temperature of the filament increases, what happens to the resistance of the filament? So as the and the current. So we're looking for I and R. And we know that as T increases, as the temperature increases, the resistance is going to increase. If the resistance increases just from V equals IR, we know that the current is going to have to decrease for the same voltage.